You should already be familiar with the idea that a charged particle experiences a force when it moves through a magnetic field. You can see the direction of magnetic field in this example is into the page. That magnetic field is a vector quantity. The velocity of the charged particle is also a vector quantity. And we say that the force exerted on the moving charge is also a vector that's found by taking the cross product between the charge's velocity and the magnetic field. In this example, since the charge is indicated as a negative charge, if you use the right-hand rule, point your thumb in the direction of the velocity vector, point your fingers in the direction of the magnetic field into the page, and then your palm faces up. That would be the direction of force if the charge were positive. Your knuckles should be pointing toward the bottom of your page, and that's the direction of force on this negative charge. So what happens is the charged particle starts to curve in this direction, but now the velocity vector points down at an angle. So if you put your thumb pointing tangent to that direction and your fingers are still pointing into the page, then you find that the force now doesn't point straight down, it points a little bit down and to the left. And the end result of all this is that as long as the magnetic field extends uniformly everywhere, the charged particle is just going to move around in a circular path, and this force happens to be a centripetal force. And the radius of curvature, as you probably already know, is equal to mv over qb, the mass of the charged particle multiplied by its velocity divided by the charge and the strength of the magnetic field. So a stronger magnetic field would produce a tighter radius of curvature, or a charge that moves faster would go with a greater radius of curvature. Okay, what we want to get into now is a similar form of this equation that says F equals IL cross B for the case of charges that constitute current flowing in a wire. So let's picture the same magnetic field. Draw a bunch of X's that represent magnetic field pointing uniformly into the page. And then we'll picture a wire. Change the thickness of my pen. Okay, so maybe, oops. We've got a wire placed horizontally in this magnetic field, and we'll say that the current is flowing to the right through this wire. So we can actually derive the equation F equals ILB from the equation F equals qvB. So let's picture the little charge carriers, all the free electrons. Maybe this is a piece of copper wire. Okay, all the little electrons would be drifting with a velocity to the left if we say the current is flowing to the right. How about this? The force per electron, I'll call that F subscript E. So the force per electron in magnitude would just be equal to the charge of an electron times its drift velocity times the strength of the magnetic field. But you don't just have one electron, you have several electrons. So we'll let capital N represent the total number of electrons traveling in the wire, which we could calculate by multiplying the charge density, the number of electrons per unit volume, times the volume. So let's see, the volume of our wire, if it has a cross-sectional area of A and a length of L, then the volume of our wire is just the product of A and L. So if I multiply the number of electrons per unit volume times the volume, then I get the number of electrons. So if I want the total amount of force, then I need to multiply the overall number of electrons that are drifting times the force per electron. So I need to multiply N, A, L, there's the number of electrons, times the force per electron, which is Q, V, B. Now you might start to see something familiar. See if I took the product of N, Q, V, isn't that just what we call the current density? So we have F total on our wire is equal to nqv times A, L, B, right? Everything else that remains. But this is J, current density, the number of amps per square meter flowing through the wire. Okay, so we've got the total force on the wire is J times A times L times B. But then if I multiplied current density times area, that would be the current. So what we really find is that the total force is equal to the current times the length of the wire times the magnetic field, or at least the magnitude of the force. Let's figure out the direction. So just pick any one of these electrons and use the right-hand rule. So point your thumb to the left in the direction of this velocity vector. Point your fingers into the page in the direction of the magnetic field as indicated by the X's, right? Thumb is going to the left, fingers are going into the page, and your palm faces down, so you might think, oh, the force on this wire is going to be down, but keep in mind, you just found the direction, you're trying to find the direction of force on the electrons that are drifting. Since those are negative charges, you should be looking at the direction your knuckles are pointing. So when your thumb points to the left and your fingers point into the page, then your knuckles point toward the top of the page. So the force on this wire is up. But another way we could say that is that the force is equal to the cross product of I, L, and B. So actually, this is kind of interesting. Current is not a vector quantity, but when you multiply the current times length, then you get a vector quantity. So if we say the current is flowing through the length of this wire, we can divide the wire up into little bits ds. The current that flows through that little segment ds is the same current flowing through that little segment ds, and the product of current and any length is a vector that points to the right. So do this. Stick your thumb of your right hand, point your thumb of your right hand to the right in the direction of the current, point your fingers into the page in the direction of the magnetic field, and you see that your palm faces up. So there's another right-hand rule. We can find the direction of force on a wire by putting our thumb in the direction of the current, our fingers in the direction of the magnetic field, and then whichever way your palm is directed is the direction of force on the wire. Okay, now is probably a good time to take a little time out to make sure we're clear about the different directions that vectors can point. Since we're working in 3 dimensions, that's our x-axis, and our y-axis points into the page, and then we have a z-axis that points toward the top of the page. Top, right, in. So instead of saying to the top of the page, I say up. So here are the different directions, right? There's up, down, right, left, in, and out. I don't need to describe to you what I mean by right and left, but some people confuse up and down with in and out. Okay, so maybe you're sitting in your living room or your bedroom as you're taking notes, and if I say point your finger up, most of you would probably point your finger toward the ceiling. But up doesn't mean toward the ceiling. And in the same way, down does not mean toward the floor. Okay, up means toward the top of the page, and down means to the bottom of the page. In fact, the vector that's pointing toward the ceiling would be a vector that's pointing out of the page. And a vector that's pointing toward the floor would be a vector that's pointing into the page. So just be careful, don't confuse out with up, and don't confuse in with down. All right, let's do a quick summary. When a single charged particle moves through a magnetic field, it experiences a force that's equal to Q, V, cross B. And if we just want the magnitude of that force, we say it's Q, V, B sine theta. In the same way, we can find force on a current carrying wire by taking the cross product of IL and B. But if we just want the magnitude, we say force is equal to BIL sine theta. So let's show just a couple quick examples of how the angle between the magnetic field and the length of the wire factors into the amount of force. This time let's picture a uniform magnetic field pointing to the right. Change colors for my pen. How's that? Okay, in our first example, the current in the wire, we'll say, flows in the same direction as the magnetic field is pointing. We've got current flowing to the right in a magnetic field that points to the right. So the angle in between the direction of current and the direction of the field is 0, and so the force is equal to 0. Case number 2, we'll take that same wire. Well, I didn't indicate where the L belongs in this equation, so the L obviously just represents the length of the wire. How about, in this case, the current now is flowing up toward the top of the page. And we'll place it in that same magnetic field that points to the right. Okay, so I want you to use the right-hand rule. Take all the fingers of your right hand and point them to the right. Point your thumb up, and by up I mean toward the top of the page, not toward the ceiling. With your thumb pointing toward the top of the page and your fingers pointing to the right, your palm faces in. So in this case we have a force that points in, and the force is equal to BIL sine 90 degrees in this case, right? Current flows that way, magnetic field points that way, so the angle between them is 90. So if we recognize that the angle is 90 degrees, we're just going to say F equals BIL. Let's go over one last example. Case number 3. The wire is pointing at some angle other than 0 or 90 relative to the field. Field points to the right, and current flows up and to the right. So there's an angle theta in between the wire and the magnetic field. So what we could do is take the length of the wire and divide it into components. So if the overall length of wire is L, this is L cosine theta. There's L sine theta, and it's just the product of I and L sine theta that's contributing to the force. So if we take the product between I, L sine theta, and B, we get a force that still points inward, okay? Point your fingers in the direction of magnetic field, and instead of pointing your thumb in the direction of the current, point your thumb in the direction of the component of the current perpendicular to the field. So we get force inward and equal to BIL sine theta.